Okay, so as Jessica told you, I'm at the School of Economics, and also I'm microeconomics with interest in environmental economics. So you will see the focus of my lectures will be more in applied theory. So I'm applying theory to understand the impact of environmental policies. And also that's why also the topics are related to microeconomics. So the first topic that we will cover is the choice of policy instruments under asymmetric information. That is when the abatement costs are unknown by the regulator, but private information from the polluter point of view. So the firm knows about own abatement cost. So how you should adapt your choice of policy to this fact, the fact that you don't know the abatement cost. Then we will talk next week about, non-point source pollution. That is more generally how to include spatial issues in the choice of environmental policy. The fact that the pollution diffuses spatially, and they are between the source of pollution and the receptor of pollution. And sometimes it's difficult to, from the pollution you measure at the receptor, to figure out what are the source of pollution and how much the polluters are polluting or emitting. And so you should adapt also the regulation to this fact, with this distance and also dilution of pollution across space. And this is something we will address next week. And there is also one lecture on environmental international agreements. So transboundary pollution, the problem of transboundary pollution is that you don't have any central authority which is in charge of regulating pollution. So as you will see today and next week, we will talk about one regulator, so someone in charge of, imposing one regulation or designing and enforcing a regulation. For transboundary pollution, in general, there is no supranational authority who is in charge of that. There are some international organizations like the European Union that can deal with pollution, but still they have limited power. And one issue that you need the agreement of sovereign countries. So many regulation or environmental problems are solved through some international agreements. So the question is how to design the agreement given the sovereignty of countries. So you need the adhesion of countries. Is it possible to get some reduction of pollution, like reduction of climate change emissions, given that it is an international problem and they need the agreement of countries? That is, it should be in the self-interest of countries to sign this agreement. So in order to address this problem, we need to have some model. So we will deal with a model of basically pollution, international pollution. And we will address the issue of cooperation and coordination of emissions. And we will use game theory, mostly cooperative game theory, to address this problem. So as you will see in our 3 lectures, the background is mostly microeconomics and sometimes some advanced techniques in microeconomics. So today, what I will use is economics of information or mechanism design, especially in the second part of the course, of the lecture. And next week I will use cooperative game theory, non-cooperative game theory as well. Okay, so let's go. So feel free to interrupt me anytime for questions. So today we'll talk about pollution with private information. So we will start with some basic model. So I try to get the simplest model of pollution with asymmetric information. So I will present the model, and then I will go with the same model through two main results. So first, there is a very famous result in environmental economics about just the choice between taxing pollution or setting a cap on emissions or pollution, which is the well-known results by Weitzman about the choice between those two instruments. And this is known as price versus quantities, because what price in the sense that you set a price on emission, which is a fee per unit of emission, and quantity in the sense that you regulate according to quantity of emissions. So there is quite general result that tells you that the choice between those two instruments would depend on the slope of marginal abatement cost compared to marginal damage cost. Okay. So it seems quite technical, because you talk about slope of curves or function, but it has some economic meanings, because behind the slope you have some economic intuition about how abatement cost and damage changes when you change the level of abatement, the level of emissions, depending of the pollution problem you consider. In some pollution problem, you have like very flat damage function, or very, I will provide some example in which you may think that the marginal damage marginal damage is more deeply sloped, or the marginal cost is or the reverse. So the marginal cost is more deeply sloped. Okay. So it's a result which relies on simple microeconomics modeling. So we will go through the modeling, the math, but also try to get the intuition, economic intuition, and also go to some graph to illustrate this result. And then at the end of the course, I will talk more about a different way to regulate, which is called what I'll call contract-based regulation, which is instead of imposing a fee on emission or standard on emission or cap on emissions, you propose a menu of regulation. That is, you don't impose any regulation, but you let firms decide which regulation they want to pick. So I provide a couple of examples on that. And you design this menu in order the best way to minimize the cost and to maximize the efficiency of this regulation. So in order to address this problem of designing those contract-based regulations, we will use a mechanism design, the standard theory of mechanism design, or what is called also economics of information. I think the background of this lecture will be what you are. The course of microeconomics that I guess Amrish Patel is teaching will be the background of this lecture. So we'll go on through all these standard techniques that try to figure out how to design the best instrument, given that first it should be the firms are free to accept or not the regulation, and second, the regulations must be such that firms select the regulation that is for the tax fee and the subsidy, or the abatement level that fit with its own cost. Okay, so it's a problem in which you have a menu of regulation. You can decide about different level of abatement as a firm, and you get different fee and subsidy depending on the level of abatement you commit on. And the problem is how to design these abatement and transfers So we will provide some solution here, and I will also talk about one illustration, which is how the design of policies to protect the biodiversity or to buy forest to store carbon, for instance. And okay, so it's again a regulation which is not imposed. Landowner are free to, to sell or to convert their land from agriculture to forestry and get their compensated for that. And the question is how much, and depending on some parameter, which is the willingness to accept some compensation for, this conversion of land, which is private information. Okay, so let's move into the model. So what I need are two agents, one polluter and one victim, or a set of agents that are victim of pollution, so one polluted agent. Okay. So you will recognize, I guess, some standard model you are using in this course. So there are two ways to model this problem. You can model with emissions, or you can consider abatement as a decision choice by the firm. Okay. So I will denote it by E, the level of emissions by the firm, and there's a cost of reducing emissions, and this will be captured by this cost function, which depends on two parameters: the level of emissions. The less emission you have, the more costly it is. And private information. Theta capture some private information that the firm owns on the level of the cost. And for simplicity, I will consider two levels of cost, high or low. You can have a continuum of cost, or you can have but here you have two types of firms that are high abatement costs and firms with low abatement costs. So it's a random parameter for the regulator point of view. So the regulator does not know if the costs are high or low, but the firm knows. Okay? And those cost functions have this shape. Okay, let's. So here you have emission, and here you have euros or kronors, and you have something like this. So there is some laissez-faire or uncontrolled level of emission, which is costless. So the costs are zero for these. Emission E stands to equilibrium, like laissez-faire. But then if you reduce your emission, that is costly, and this cost is increasing and convex, and potentially infinite for zero level of emission, or it could be also finite. Okay? And you have two types of costs. You have these costs, let's suppose that, so this could be the high cost, and you can have a low cost. It could be with the same level of laissez-faire emission, for instance. This is low cost. Okay. The regulator does not know the real cost. All the regulator knows that in the economy there's a probability phi that our costs are low, and probability 1 minus phi, or nu. No, it's not phi, it's nu. Nu that costs are high. So this is common knowledge for the two partners. Also the firm knows that, the regulator knows that. So these are the properties of the cost function. Another important assumption is that the marginal abatement costs are lower with lower cost. Okay, so not only the costs are lower, but also the marginal cost. Yeah, so the regulator will observe the emissions. So the asymmetric information is not on emission, it's really on cost. if the firm has those two technologies, of course, as long as the emissions are regulated, the firm will pick the lowest cost, of course. But yeah, well, you can think about. Of course, you can complexify the model, saying that, as you say, that the cost changes across time and so on. But what I want to have is the simplest model to address. That's why you have only two types of cost, and firm is characterized by only one cost. Okay, but that could be another model. So what is important is that you can compare marginal cost. So like pick one level of emission. So the marginal costs are the slope of this cost function in absolute value, and they are higher for high-cost firm compared to low-cost firm. Okay. This is important because then you get the so-called single crossing property, which is useful in this model. And in the first part of the lecture, I will assume that linear marginal cost. So this is an example of this kind of cost function. You have like the laissez-faire emission and how much you emit. So this is, by definition, the level of abatement, how much you reduce emission compared to the laissez-faire. And you have two type of, theta has two value, high or low, and high is higher than low, okay? So this is on the cost side. On the damage side, we have only one damage function, and which is increasing in convex. Okay, the more the emission, the more the firm is emitting, the higher is the damage. Something like this. And the damage is the marginal damage is increasing with emission. Okay, so it's standard assumption that you can cope with some emissions, a little bit of pollution. But the more pollution, the higher is the pollution concentration, the higher is the impact of one more unit of emission, one more ton of greenhouse gas, for instance. Okay. And also, we will assume later that marginal damage are linear. Okay, so that will mean that the damage function itself is quadratic. Okay, and then we will consider that these two agents, the victim of pollution and the firm, are risk neutral. There is risk from the regulator point of view, because the regulator does not know the type of the firm, and so he assigns probability nu and 1 minus nu to each type, and therefore he will pick the regulation that minimize its social cost of the social cost of emission, the expected social cost of emission. So you will see. So it considers the expected social cost. The distribution, damage, cost function, and distribution are common knowledge by two. So the only new ingredient compared to what you have seen so far when you in this kind of model is that only the firm knows about the level of cost, okay, which if it's high or low. Okay, so in this framework, the first thing I do is to, as usual in economics, is to compute the first best. What will be the efficient level of emissions in this framework? And here the first best means that we are in full information. The regulator knows about the level of the cost. So if the regulator will know the level of cost, that is, the regulator will know about theta, she will choose the level of emission that minimizes social cost of emissions or abatement, which is the damage due to emission plus the cost of abating. For society, how much it costs to have this a certain level of pollution. And then if you solve this problem, given the assumption we use for abatement cost and damage, convexity, and so on, we get the solution. The solution are described by these two first order conditions. That is, take the first derivative and equalize to 0, and you get those conditions which tells you that the marginal damage should be equal to the marginal abatement. So the interpretation, as you may know, is that on this side, this is the reduction of damage from one less unit of emission or one more unit of abatement. On this side, you get what is the cost of one more unit of abatement. This is the interpretation of marginal abatement cost. And it is negative because here we talk about, the cost of emission. So the marginal cost of emission is negative because when you emit more and more units, that reduces your cost. Okay? So minus the marginal cost of emission is the marginal abatement cost, the opposite of. Okay, so in one sense, this is how much you save by reducing emission by 1 unit. Okay? So in terms of reduction of emission instead of increasing emission. Okay. Now the next question will be how you will implement this optimal level of emissions economy with the regulation. Okay, the traditional solution will be to get Pigovian tax, for instance, or an emission cap, for instance. But here the problem that the tax and the emission cap will depend on the cost, right? So if you observe the cost, you get a different tax or a different cap depending on the cost. Now, what if you don't observe the cost? Okay, what you can do under asymmetric information is to have something more fancy, more complex than a flat tax. You get a Pigovian tax, but which is non-linear. So in the same spirit than in the Pigovian taxation, than with Pigou, the tax will reflect the social cost of emissions. So if you tax something which is the damage, you tax as a rate which is equal to the damage function plus or minus some fixed constant parameter, then you get the first best. Then you provide incentive for firms to emit at the first best. Why? Because then when the firm decides about how much to emit, then the firm will solve this program. The firm will minimize its cost of emission, this is a technical cost of abating, and also the cost of emission from a regulator point of view in terms of regulation. This will be the tax rate, and that as well. So you can have a constant just to make sure that, for instance, that for instance the profit of the firm is positive. You want to still the firm to be into business. Solving this problem, the firm will equalize marginal abatement cost to marginal damage. So my point was to say, let's get to some non-linear tax. A tax which depends on emissions, but in a non-linear way. Okay, so not more complex. So the traditional tax function will be with a per unit tax will be just to multiply the per unit tax by the level of emission. Here the problem that the damage function is convex, so it's not linear. Okay. So you want to mimic this damage function with the tax rate. Again, the idea here is that the firm realize the social cost of its own action, the fact that the firm is emitting. So you want to match this damage, so you make the firm pay for the damage. And then you can add some constants. So, like for instance, you can divide by some get some reduced fee. Okay, so you get something which is make it pay for the damage minus some. So it's like an income tax. When you pay your income tax, this is something which is non-linear. You know, your tax rate depends on your revenue on a non-linear way, for instance. Yeah, okay, so that's the next step. Okay. Now, what is the problem of the firm? Okay, the problem of the firm is to minimize what? So the level of emission will impact two things. One, the cost of production, okay, plus how much the firm has to pay in terms of tax. And then if you substitute the tax rate by this, you end up with what you get. Okay, and then the solution will be, if you solve this problem, you get the first order condition here and the first best. Yeah. Yeah, that's true. So then, but you can have something a little bit more complex. Yeah, but what you can do, you can make the tax depend on the emission from others, right? So the problem that when you have several firms, the optimal level of emission depends on the emission of all firms. So then you should have tax rate will depend on how much the other emitted. Which is, yeah, it's illegal, of course. But the idea here is that you can potentially have implement the first best with something which is quite complex. Something people sometimes don't realize that you know, here you can implement the first best by and the reason why you want to implement the first best here is that you are limited to some instruments. So you are constrained to get some flat tax, for instance, or only one cap on emissions. Okay. That's why you cannot implement the first best here, for instance, in Weizmann result. But people tend to forget that this is one way to implement the first best in this kind of model. And this is the same spirit than Pigou, the Pigouvian taxation, just make the firm internalize the social cost of its behavior through the tax rate, which is quite complex here. Okay. Now, if you are limited to a cap on emission, what is the best cap? Okay. First, how the firm will react to a cap on emission. The problem of the firm is to choose a level of emission that minimizes cost, given that the firm has to comply with this cap. So it's an emission standard. The firm is not allowed to emit more than some level of pollution. And as long as this cap is binding, that is, it is costly to reduce emission to this cap, the constraint will be binding, and the firm will emit just the cap, as long as it is costly. So the story is as follows. Set a cap here. The firm is not allowed to emit more than this cap, then therefore the firm will pick this level of emission. And the cost of complying with regulation depends of the type of the firm. If the type is if the firm is of high cost, this is the cost, high cost firm, and this is the cost for the low cost firm. Okay. So you will end up with the same level of emission, which is a cap. This is how the firm will react to this regulation. Now let's go to let's design the regulation. What will be the cap chosen by the regulator? The regulator will decide about the cap which minimizes the social cost of pollution. And here, because the regulator does not know if costs are high or low, the regulator will get the expected social cost of emission. That is the expected cost plus the damage. So the regulator knows that the firm will stick to the cap, therefore the damage will be the same, whatever is, regardless of the cost of the abatement cost. But the cost depends on whether the firm is a high cost or a low cost. So therefore the regulator takes the expectation about the two types of curve. And then you get a different first order condition compared to the first best. That is the cap on emission will equalize the marginal damage to expected marginal abatement cost. So I can draw a nice picture out of that. So let's do this. No, this one. So this is emission. Let's write down, let's say, for instance, some marginal abatement. Let's just want to be sure to be consistent with my picture here. So let's do it here. So you have this is marginal abatement for high cost firm, and this is marginal abatement for low cost firm. And this is the marginal damage. Okay? And now you can get the average. The average is in between, and depending on the nu and 1 minus mu, it's closer to the high cost or low cost. So this is the average marginal abatement cost. So this first condition tells you that you should cap emission at the level where the marginal damage crosses the average marginal abatement cost. Okay? If you do that, the firm will emit up to this cap, and therefore that will be the marginal abatement cost for the low cost firm, and this will be the marginal abatement cost for the high cost firm, okay, which is quite higher. So that will be the best you can do given asymmetric information with a cap. This is the story. Now, we're going to compare this emission standard or emission cap with the best tax. But before that, I just want to mention to compare this cap with the first best. Remember, the first best will be to equalize marginal abatement to marginal damage, but the problem that marginal abatement depends on the type of firm. So the first best is differ if costs are low. This will be the first best emission with low cost, and this will be the first best emission with high cost. So if there are high cost of abatement, you let the firm emit more because it's more costly to abate. Okay. So here you get something which is in between. That means that you are always wrong. Whatever is the type of the firm, you are wrong compared to what should be done. But sometimes you are wrong, I mean, depending on the type, you are wrong in the wrong direction, in the opposite direction, let's say. So if it's cost higher than expected, your cap is too stringent. You want the firm to reduce emission more than what it should be optimal. So there is under emission compared to the first best. And if costs are lower than expected, it's the reverse. The cap is not stringent enough. That is, the firm will bind the cap because it's costly to abate. But it should be the firm should emit even less. The firm should abate more. Okay. So if costs are low, there is over emission compared to to the first best. So with scores are high, under emission compared to the first best, scores are low, lower emission compared to the first best. Okay. You will see that with the tax rate, with the fee on emission, you get the reverse. Sometimes this level of standard is called the ex ante efficient emission level. Why ex ante? Because it will be the efficient level, emission level, if you won't know the right abatement cost. So from ex ante in the sense that before you know the right abatement cost. Whereas these two levels are the ex post efficient level. That is, once you know the real abatement cost. Okay, now suppose that instead of setting a cap on emission, which is called the quantity regulation in a Weizmann term. So I mean, by the way, if you this famous result is derived from a famous paper by Martin Weizmann, which was published in the '74. And this paper compare the central planning of Soviet Union compared to the market economy. And the quantity regulation was the regulation by central planning in communist countries. And the tax regulation was the price in the market economy. So if you read Weizmann, the text in this, you have this introduction. The focus is really comparing two systems. One based on quantity, you plan production, and the other one based on prices. That is, the market itself sets on price. But of course, in the same paper, he talks about also environmental regulation, and finally, this paper is very popular in environmental economics about regulation. So here we talk about price regulation. Instead of setting a limit to the quantity of emission, you set a price, a fixed price on emission. And here the problem that the price per unit of emission is constant. Yeah. So it's a fee tau. So again, how the firm will react to this fee? The firm will do as before, minimize cost, but now the cost here now is just tax per unit of emission times the level of emission. Okay. So for a level of tax tau, the firm will equalize marginal abatement cost to the level of tax. So this is a first best reply to some level of tax. Every time you increase tax, the firm will modify the emission, but in a way to equalize the marginal abatement to tax rate. And this is regardless of the type, regardless of if the firm is of high cost or low cost. Of course, the cost will depend on that, but this behavior does not depend on the cost. Okay. So as a regulator, you are smart enough to take into account this future behavior of the firm. So what you do, you choose a level of tax that minimizes the expected cost of emissions in expectation regarding of the type of the firm, subject to this best reply function of the firm, subject to the fact that the firm will always equalize marginal abatement cost to the tax rate. So you minimize this subject to this first order condition above. So at the consequence, when you solve this problem, you get this first order condition. So here in this term is the marginal social welfare when emission changes. It depends on the type, and also, as you can see above, emission will depend on the type of the firm, on the cost. So every time you change emission, this will affect the social welfare. This capture how the social welfare will be affected. And this term is how emission will change when you change the tax rate. So in order to get this equation, you take the derivative with respect to the tax rate, given the constraint above. Okay. Now we assume that the marginal abatement cost was linear here. Okay. So remember, we had this assumption about. Let's write it down here. Sorry, I'm moving a lot. So marginal abatement. So we had the assumption. So marginal abatement is therefore linear. Okay. So when you take so then the firm will react by equalizing tax rate to marginal abatement. So let's denote the level of emission for a given tax rate and a given type theta, E tau theta. You want to know how emission will change. So another way to write it down is that way. So you want to know how emission will change when you move the tax rate. Therefore, you take the full derivative, and therefore you get t of theta. Sorry. So therefore you get okay. So this is how emission vary when you vary the tax rate. So if you plug this in the first order condition, you end up with those conditions. Okay. So believe me, you can do it by yourself. By the way, I will give you at the end of the lecture some problems in order for you to do that. So this is what you get at the end. You get that the first best, the tax rate equal to the expected marginal cost and also the expected damage. And it turned out also that it is equal to the marginal damage at the ex-ante efficient level. Okay, so this is something which is very helpful because here in this picture, remember that the cap will be the ex-ante efficient level of emission. Okay, that's the one which equalizes the marginal damage to the expected marginal abatement. So this is the ex-ante efficient level of emission. To find the optimal tax rate, you pick that and you equalize this to the tax rate. So the condition that the marginal damage with the ex-ante efficient level of emission equal to tax rate gives you the tax rate. You get the ex-ante efficient level of emission, you compute the marginal damage, and you get the tax rate. Okay. So under those assumptions about cost and damages, what is nice is that you can easily compare in the same graph the two types of regulation, a cap on emission and the tax rate. Right? What you do, you plot the expected abatement cost, you plot the marginal damage, and you say, okay, there's two ways to relate. You can have a cap on emission, or you can have a tax. And this is the best tax, and this is the best cap, given that there is asymmetric information. And those two are based on the ex-ante emission level, efficient emission level. Now, the two instruments will have different impact on emission. If you have a cap, as I said, you are sure to get the cap every time, but the costs are not the same. If you have the tax, what happened? With this tax level, the firm reacts by emitting such that abatement cost equal to the tax rate, right? So with this tax rate, the firm will choose the level of emission that equalizes the abatement cost. Suppose that consider the firm of low type or low cost. That will be how much the firm will low cost will emit. But if the firm is of high cost, the firm will emit this. Okay. So you will have two different levels of emission, one for the low cost and one the high cost. And compared to the first best, you get under emission for low cost and over emission for high cost. Why? But because you have designed as a regulator the tax based on expected cost. So the tax reflects the ex ante level of emission for expected cost. But it turned out that, let's say, that costs are lower than expected. So when the firm equalizes the marginal cost to the tax rate, which is based on some expectation, the firm emits less because it's cheaper to emit compared to the expectation. So the tax reflects the expected cost, but the costs are lower, so it's cheaper to emit compared to what was compared to what that was expected when you design the tax, and therefore the firm emits less, the firm abates more. And it's the reverse for high-cost firm. The cost is higher than expected. The tax was designed for the lower cost than the real cost, and therefore the firm emits more than what it was expected. So you have, opposite. So to conclude before the break, what you can take from that is that in both cases you are wrong. You never implement the first best. So you are, as a regulator, you are doing you are misleading. You are doing a mistake, but depending on the instrument you choose, the mistake can go in one or the other direction. You can, okay, and it depends also on the on the cost of the firm. Okay. So now, after the break, what we'll do, we'll compare those two regulations. In order to compare those two regulations, we have to compare the welfare loss due to each regulation. And by comparing those welfare laws, we will be able to do which instrument is better than the other one.